In this video, we're going to begin by talking about private solutions to externalities. We left the last video, we talked about government solutions to externalities. There's a number of things in terms of the private side that you can do. First of all, particularly with the advent of the internet, we see these shame and frown campaigns where companies that pollute, their pollution is made public, quite public on the internet, so that others can see, and it creates powerful new norms. Companies want to look like they're responsible stewards of the environment, so these norms can be very powerful in getting people to clean up their mess. In other cases, there's firm ownership of multiple businesses. So let's say bees are really important to apples in terms of their germination, because bees carry pollen. So what you may find is you'll find these beekeepers that travel around the country that use their bees to help, particularly fruit farmers, to do the pollination of the apple trees and other types of trees. So what would happen is those bees have a positive externality. The apple orchard guys would just buy the beekeepers. So they just buy them and bring them in, and therefore they've internalized the benefit of the bees. And then ultimately you have charities as well. Charities like the Sierra Club and other type environmental groups, Greenpeace, all these different groups that rely on donations to not only one, have a shame frown campaign, but also two, to clean up messes in the environment. Now, in terms of these private solutions, we have what's called the Coase theorem, which is named after a famous economist who looked at these private solutions and said that, hey, these efficient private solutions will always occur to fix externalities so long as the transaction costs are not too high. So what he's saying here is transaction costs are the agreement costs, like how much does it cost for lawyers to bring up the contracts so that these things get resolved, and then how hard is it to enforce and catch cheating. If those aren't too high, then we'll almost always find an efficient private solution, because the people downstream aren't going to rely on the government to clean up the pollution from the guy up the stream. They're just going to take this guy to court and say, hey, look, you're either going to pay us or we're going to come up with a solution to this. So there are private solutions where the government doesn't have to get involved, and that's what's known as the Coase theorem. Okay, now switching gears here, we're going to talk about types of goods. Typically in economics, particularly Economics 2200, we were really talking about private goods. And I'll give you an example of how we could characterize private goods. There's these two characteristics. We have excludability, which means the owner of the good can stop its use by others. And then we have divisibility, which is also known as rivalrous as well, where one person's use diminishes another person's use. So in terms of these private goods, let's take an example of a private good like chocolate. Is chocolate excludable? Yes. If I own chocolate, you can't just take it from me. The law says it belongs to me. You can't take it. And two, is it divisible? Yes. If I start chewing on it, of course, you're not going to want to eat it after the fact. So chocolate's a good example of a private good. Now let's say we can't exclude somebody from it, but people's use of it does diminish, and we have what's called a common resource. So here we have something like the ocean. No, I can't stop anyone from going out in the ocean. It's open. Nobody owns the ocean. But if everybody overfishes the ocean, then the common resource is going to have less fish, and it's going to become depleted as an asset when we think about it economically. So we have this thing called the tragedy of the commons. Because nobody owns the commons, because it's common to all, the commons tend to be depleted of their resources. Then we have the next over here, we have divisibility. No, you can't, one person's use doesn't diminish another person's use, but it can be excludable. These are quasi-public goods. So think of a toll bridge. Yes, I can stop you from using it if you don't pay the toll, but no, your use of the toll bridge doesn't diminish someone else's use of the toll bridge, unless thousands and thousands and thousands of people back up on the bridge trying to get across it in terms of traffic. So that does diminish its use somewhat, but not quite what we're looking for here. So that's a toll bridge is a good example of, yes, it's excludable. No, it does not diminish in quality. These are also called natural monopolies. And then the last good that we have is a public good. And that's where I can exclude somebody from enjoying its benefits, and their use of those benefits doesn't diminish. So we can think of a lighthouse. A lighthouse is a good example. Is if it's turned on, can I stop you from seeing it? No, I can't. And does you seeing it diminish someone else seeing it, their their ability to see it in just as good a clarity as you can? No. So that's an example of a lighthouse. What we find, though, is this free rider problem, because I can't stop you from using it, and it doesn't diminish. Ships at sea may pay for the service of that lighthouse so that they don't run into the rocks or get lost in the fog. Whereas you, in your small rowboat, you may not pay for it, but you still free ride on it because of the big ships paying for it. So you get something that you didn't pay for. Another good example is national defense. Can we exclude anybody in the United States from enjoying the freedoms the U.S. military provides? No, because if you live in the U.S., you're under the umbrella of the military. Is it divisible? You know, does your feeling of protection in America, does it diminish the quality of national defense if others are enjoying the same level of protection here in America? No, it doesn't. So it's another good example of a public good. All right, now we're going to walk through a mathematical example of an externality. In the last video, we talked about externalities in terms of graphically showing you what they look like. In this case, we're going to show how an economic tax, a Pigouvian tax, can actually make a situation better. So begin with, for example, we have two paper plants located on a river. The upstream firm, firm X, has a production function. X's production is 2,000 times the square root of the number of workers who are at their plant. The downstream firm Y is affected negatively by firm X's discharge of chemicals into the river if that exceeds the river's neutralizing capacity, which we call XO. So firm Y has a slightly more complicated production function. If the amount of production that X produces, firm X produces, is greater than that neutralizing capacity, then firm Y has a production function of 2,000 times the number of 2,000 times the square root of the number of workers that it employs, but then it's also multiplied by firm X's production minus that neutralizing capacity raised to some power alpha, which is basically the factor which shows how powerful that externality is. And if firm X's, the upstream firm's production is less than the neutralizing capacity, then all is good. Firm Y is not affected, because when the river water gets to firm Y, it's just as good as it was for X, because it's less than that neutralizing capacity. So the river's effectively clean when it gets to Y, and so Y's production function is 2,000 times the square root of the number of workers that it employs, which is the same as X. All right, now we're going to give some more information here. Let's say the price of paper is $1 per linear foot, and wages for workers are $50 a day. So if we assume that alpha is 0, that there's no externality, so there won't be any externality in this case, so this is the base case, then both firms maximize profit when the wage that they pay to their workers equals the marginal revenue product that each worker brings in. So the marginal revenue product is really, if we remember, the revenue of something's price times quantity, so it's the price of paper times, and because we're talking about the marginal product here, we're talking about the change in quantity produced divided by the change in one worker. Okay, so if we change one worker, how much more quantity is produced? So price we know is $1. We multiply that times the change in quantity produced over change in worker. Now, where did this come from? Well, this equation, came from, and it's 1,000 over the square root of L. It came from taking this equation right here and taking the derivative. In this course, because calculus is not required, I wouldn't ask you to do that on the test. I would just give you this information. But if we did take the derivative of X here, we would have the half power come down, which would be 2,000 divided by 2, which would make it 1,000. And then because it was taken, the derivative was the number of workers to the half power would be now the number of workers to the negative half power, which is why it's on it's in the denominator here. We know the $1 here just multiplies through. So we can see here that the marginal product of labor is then 1,000 over the square root of the number of laborers. We said that both firms maximize profit at W, which is the wage. So we set it equal to 0 because that was a given piece of information. And when we solve for the number of workers, since it's the same for both firms here and here, because remember the externality doesn't exist in this case, both workers would employ 400 people each, and both workers would produce 40,000 feet of paper each. So that's the base case. So now let's assume that there is an externality, so that alpha here in Y's production function is negative 0.1, and the neutralizing capacity of the river is 38,000 feet of paper. Any more than that causes pollution. So in this case, we can see firm X still hires 400 people, just like they did up here, and they produce 40,000 feet of paper because that's what maximizes profit for them. So clearly 40,000 feet of paper exceeds the neutralizing ability of the river by 2,000 feet of paper to clean itself up. So there is pollution in the river. So now firm Y faces a new situation. Remember, they produce where the marginal revenue product equals the wage. So we take this equation up here. We then put we then take the derivative of this right here. This is their production function. We take this derivative and we end up with this equation. And when we set it equal to wage, which is 50, we end up with the number of workers is not 400 like before. Firm Y can only hire 87 workers, and it can only produce 8,723 feet of paper, whereas before they had 40,000 because the river is polluted when it gets to them. So therefore, total production in the entire economy, when you add firms X and Y together, is only 48,000 feet of paper and only 487 workers, whereas before it would have been 800 workers and 80,000 feet of paper. So clearly, X's production causes a negative effect on Y and society as a whole. So how do we find efficiency? Well, we use that corrective tax, which we'll denote as T. And in this case, we want to find the tax rate that will incentivize firm X, so we're going to tax firm X, to produce 38,000, which is the neutralizing capacity of the river. And if they produce at 38,000, if you plug that into this equation up here, you'll find that